Howdy, nerds. Howdy. Welcome back. We're going to finally finish section 1.2. Let's knock this thing out. All right, we're going to finish up by talking about asymptotes. First, we're talking about horizontal asymptotes because they're the more difficult ones, so why not get them out of the way first, right? Something is a horizontal asymptote if it is a horizontal line, therefore y equals some number, that our graph is approaching as x gets really big or x gets really small. Like this graph right here that I showed you a couple days ago. This line is y equals 1. And because our graph is approaching it to the far left or the far right, in fact it's both for this one, because our graph is approaching it as we go to the far left or the far right, and it is y equals a number, we say that is a horizontal asymptote. Cool? Okay, now, there are tricks to finding these horizontal asymptotes. And these tricks involve the degree of the numerator and the denominator of a rational function, meaning if you have x's in the bottom, that's really going to be when we talk about asymptotes the most. Are there other functions that involve horizontal asymptotes? Sure, exponentials. Are there other functions that involve vertical asymptotes? Sure, logarithms. But for now, we're going to be talking specifically rational functions, things with x's in the bottom of a fraction. Okay. So the degree of a numerator or the degree of the denominator is what's the biggest exponent in that area. So here, this numerator is a degree of 3. This denominator has a degree of 2. Okay? That's what we're talking about. So, first trick. If the denominator, the bottom, has a bigger exponent than the top, we could be cheesy and call this a bottom-heavy function. Bottom-heavy. So, bigger exponent on the bottom. Automatically, y equals 0. The x-axis will be your horizontal asymptote. So if you have a bottom-heavy function, x-axis, every time, okay? But if the biggest exponent on the top and the biggest exponent on the bottom are the same, then what we're going to have to do is we're going to have to build a fraction. Y equals leading coefficient over leading coefficient. And the leading coefficient is the number that sits in front of the x with the biggest exponent. And we have to say it like that because sometimes they're out of order. Like you can see this one's out of order. And that's out of order. The leading coefficient down here is -1 because it's in front of the x with the biggest exponent. So we just have to watch for order. But anyway, if the degree of the top and the degree of the bottom match, then you just do leading coefficient over leading coefficient. So it's not bottom heavy, it's not top heavy. That is how you find your horizontal asymptotes. Cool beans? I'm going to predict, Mark, that your question is, what if it's top heavy? We got a box at the bottom of the paper for those. So those are a very special thing. But I will tell you this. If it's top heavy, you don't have a horizontal asymptote. Let's go there for now. Okay? The easier things to find are going to be our vertical asymptotes. The line x equals a, which means x equals some number, is a vertical asymptote of our graph if the y values approach a positive infinity or a negative infinity as we get close to that number. So go back to the one that I showed you. Here we are. This graph has 2 vertical asymptotes, just reminding you what the vocabulary for that is. Infinite discontinuity. Okay. Notice that if I'm on the left of this vertical asymptote, my graph shoots up to positive infinity. If I'm on the right of my vertical asymptote, my graph shoots down to negative infinity. It could do both or just go to one of the 2 infinities. It doesn't matter. If your graph heads to one of the infinities as it gets close to a value of x, you have a vertical asymptote. For rational functions, things with x's on the bottom, those are going to only occur when there's a number that would make you divide by 0. That's the only time a vertical asymptote can happen, when you have x's on the bottom. But we have to be very careful, because occasionally things that give us 0 on the bottom could be removable discontinuities, so by definition, not a vertical asymptote. There'd be a hole in the graph. Let me track down my graphing calculator real quick. Okay, I got it. I would like to show you one of the things from yesterday's extra credit, one of the find the domain questions. And I'm bringing this up, 1, because it's going to be good notes, and 2, because a lot of you did them wrong, those particular questions, finding the domain. And we're going to want to make sure that we're better at those before the assessments come up. Anyway, we go to y equals, I got to clear that junk out. The one in particular that I'm talking about was x minus 2 over x squared minus 5x plus 6. I'm going to factor the x squared minus 5x plus 6. That's what you would have gotten when you factored. So right now I have 2 numbers that make the bottom equal 0, right? But if you hit graph, I'm going to hit zoom 6 because I don't remember what screen I was looking at last time. I don't have 2 vertical asymptotes. I have a single vertical asymptote. And that single vertical asymptote is happening at x equals 3, which I hope that you could see is happening right there. So why? Why did that occur? Well, it's because this graph has a removable discontinuity at x equals 2. The x minus 2's on the top and bottom cancel each other out, leaving us with this. I'm going to hit graph, and you're going to see the red one trace over the blue one. Mr. M, looks like the same graph to me. Okay, it looks like it. So here's what I'm going to do. I'm going to hit second, and then the graph button, which takes me to the table of values that this thing is going to show you. Now what this table does is it shows you what your y values are at certain x values. And I have to scroll up in order to see that these two functions are not the same. You'll notice right there, the blue one throws an error at x equals 2, but the red one doesn't, proving to you that they're not the same graph. The blue one has a removable discontinuity at 2, -1. And I know it's -1 because that's the y value it wanted to have. But it's not a vertical asymptote. It's a removable discontinuity. Cool? So yes, anytime you have a vertical asymptote for a rational function, it's because you tried to divide by 0. But that doesn't mean every time you try to divide by 0, you get a vertical asymptote. It's a one-way street. Because occasionally, they're removable. Cool? So we just got to watch out for those. All right. We're going to want to factor everything that we can factor. And luckily, x squared minus x minus 2 does factor. The two numbers that will multiply to -2, that'll add to -1 are -2 and +1. As you can see, nothing is going to cancel out. That means I still have 2 numbers that make the denominator equal 0. Both of those numbers are going to generate a vertical asymptote because nothing is canceling out. So the vertical asymptotes, which are very easy to track down, are going to be x equals. All vertical asymptotes are x equals. You have to say x equals because if you don't say x equals, you don't have a line. You just have a number. But if you say x equals a number, well, that's a vertical line. I have x equals -1 and I have x equals positive 2. When we were talking about the domain, this graph's domain is every single number except for -1 and positive 2. So we would need to string together 3 different intervals using unions. So I would have -infinity to -1, parentheses, union, parentheses, -1 to 2, parentheses, union, parentheses, 2 to infinity. I had a lot of questions with the extra credit. Well, what about this x on top? The x's on top are never going to affect the domain. All they do is tell you where your graph crosses the x-axis. But that's for a later lesson in the year. I just wanted to bring it up because people asked me yesterday. So this function, would you say that it's bottom heavy, top heavy, or equal degree? You could just shout it out as a class. Bottom heavy. Since it is bottom heavy, meaning the exponent on the bottom, which is a 2, is bigger than the exponent on the top, which is a 1, guarantee we have a horizontal asymptote, and guarantee that it is the x-axis at y equals 0. X on top, and x minus 1, x plus 2. Oh, I switched my plus and my minus, didn't I? Notice how I just stopped my calculator dead in its tracks and it stopped graphing? Have I taught you how to do that yet? You try to shut the calculator off. If you try to shut it off, it'll stop. Y equals, sorry, that was a plus sign and this was a minus sign. There we go. Try to shut it off with second on. Just like the old school, what is it called? Scientific calculator. The one that's solar. Second on shuts it off. No, not one either? Yep. See, it's got off. Yep. Okay, so here we go. You can see you have a horizontal asymptote where your graph is approaching the x-axis on both sides. And you can see you do have 2 infinite discontinuities, 2 vertical asymptotes. Once again, I know I covered this the other day, but I'm just repeating it. It's not an issue that this graph crossed over its horizontal asymptote. That's not a problem. Happens all the time. Not every time, but it happens a lot. Vertical asymptotes, yeah, you're not allowed to cross those. Those are big fat no-nos. Those are literally domain gaps, places where your function can't exist. Horizontal asymptotes are just a goal. They are telling you where the graph is heading towards when the x's are sufficiently large. Okay? Now, I feel like this would have been a better example that we're about to do if I altered it a little bit. I wonder if I should. Nah, it's all right. I'll just describe it and show it to you on the calculator. First things first, factor everything. The numerator of this function is out of order, and that bothers me. I'm going to put it in the correct order. And we already know what the bottom factors to, but I'm just going to write it out like this real quick. The reason why I wanted to put the numerator in the correct order into what we'd call standard form, and that'll be in the first lesson of chapter 2, is because it shows you that your leading coefficient is negative. And I want my students to be in the habit of pulling a negative GCF every time the leading coefficient is negative. It'll just make things better in the future. So when I factor the numerator, I'm not going to say x is the GCF. I'm going to say it's negative x. There. And the bottom is unaffected. It was still going to be x plus 1, x minus 2. Once again, the reason why we factor everything is because we want to see if there's going to be any removable discontinuities. The removable discontinuity would have happened if I had to cross an x off of the top and bottom. But since nothing cancels, what we're looking at are the same 2 vertical asymptotes as before. This function has the exact same domain as the one we had just a moment ago. But we do now have a different horizontal asymptote. The reason why? This function is not bottom heavy like this one was. this function has the same degree on the top and bottom. So our horizontal asymptote will be y equals this leading coefficient of -2 divided by this leading coefficient of 1. So y equals -2 is now our horizontal asymptote. Let me show it to you on a graph, and then we'll look for questions from the crowd. Let's see what we got. So we're expecting two vertical asymptotes and a horizontal asymptote at y equals -2. Let's see something parabolic in the middle. It's not actually a parabola, but it's just a nice way of describing that shape. There you go. And just to drive home the idea, actually, I'll just leave that one. I forgot the negative button. There we go. I was going to regraph the whole thing. Crud. Yes?
Okay, so to be clear, so for the vertical aspect or whatever, it's just what x equals on the bottom.
So vertical asymptotes are going to be x values that would have given you a 0 on the bottom,
okay,
because you can't divide by 0.
Okay.
Mm-hmm.
And then for the horizontal portion, it's the exponent.
So for the horizontal asymptotes, you're looking at the exponents on the top and bottom. If the bottom has a bigger exponent than the top, automatically x-axis, like the first one. And if the exponent on the top and bottom are equal, like in this example, then it's just leading divided by leading. And you know what's interesting about this image? If you look on the left side, it appears as though the blue line stays below the horizontal asymptote. But if you look on the right side, it looks like it hits it. So it makes me curious. I wonder if this graph crosses that horizontal asymptote on the right side, but then comes back down towards it. I actually don't know. It just makes me curious because I'm nerdy like that.
So when it's bottom, it's just like y equals 0.
Yep.
Every time?
Every time. The reason why the bottom heavies go, so it's a little bit more of an advanced concept, but let me show you why the bottom heavies automatically go to 0. When we have something like this, and I'm just going to put a x over x squared. We're not even going to worry about pluses and minuses, other numbers. This is bottom heavy, but this reduces to this, right? Okay. When we talk about horizontal asymptotes, we're talking about extreme values of x. So x's that would look something like this. Now, if you had to describe that number to me, give me a one-word description.
Large.
No, this number is large, but it's the value of this fraction, very small. Yeah, that's 2 words, but yes, very, very small. In fact, the bigger this number gets, meaning the further away from 0, and if you could ever say getting closer to infinity, because that's not possible, but you know what I'm saying? The closer this number gets to the number 0. And that is why bottom heavy always goes to 0, because it makes the bottom, if you could imagine that getting to infinity was a race, the bottom's going to get there much faster than the top, which will make our y values very tiny over time.
Okay.
And if they're the same on the top and bottom, when the values for x are really small, this plus 1 and this minus 1 make a big difference. But imagine x was 10 billion. If you did 10 billion plus 1 divided by 10 billion minus 1, the value will be darn near 1. And the reason why it's darn near 1 is because this leading coefficient is a 1, and so is this one. So really, when we're talking about horizontal asymptotes, we're talking about the x values become extreme. So what's the graph start to look like? Okay.
I know it's all this now.
Okay. Okay, that's understanding why. That's why these tricks work, rather than what the trick is.
Now I started getting it. Yeah.
Now, a couple minutes ago, Mark specifically asked me about top-heavy functions. Here they are. When you have a top-heavy function, you will not have a horizontal asymptote. Instead, what you'll have is what we call an end behavior asymptote. Awful lot of talking. You'll have an end behavior asymptote. And the reason why we call it the end behavior asymptote is because we're talking, once again, like I was talking with Nyla, extreme values of x. So numbers to the far right, numbers to the far left, we describe these as the ends of the graph. All right. What that means is, technically, horizontal asymptotes are themselves end behavior asymptotes. Anything that talks about what's the graph doing as x gets really big or really small is technically end behavior. So I often just call these EBA, end behavior asymptotes. So if it's top heavy, I'll just say EBA. And I kind of already dipped into this a little bit with Nyla on the paper just a second ago. Look at this example. This is the graph of what x to the fifth over x squared minus 2 looks like. The dotted line would not be there. The dotted line is x to the third. What's happening is when our x values become extreme, I mean, they're just unreal big, okay? Like 1 with 1,000 zeros written after it, raised to the fifth power, divided by 1 with 1,000 zeros squared, minus 2. What's happening is this minus 2 has very little effect on the overall value of the number. So this squiggly equals means approximately. So if x is large enough, numbers like minus 2 or plus 5 mean almost nothing. And they could literally be forgotten if you want to think of it that way. All it's describing is what's going on at the extremes. It doesn't tell you anything about in the middle. It tells you nothing about the middle, which, by the way, is why graphs can cross their own horizontal asymptote, because that'll happen in the middle somewhere. It'll never happen at the extremes. Anyway, sometimes I use money to describe this. I go, imagine you're the richest person on the planet. So rich, you could buy the planet. We're talking about you're that rich. That's how much money you walk around with on the daily. You're that rich. If you were so rich that you own the street you're walking down and every person that's walking down it as well, and a couple dollars fell out of your pocket, you wouldn't care. Now, it's always a guy in the room that goes, oh, you would. Of course you would, whatever. Anyway, but let's be real. You wouldn't. You're that rich. You're so rich that a couple dollars mean diddly. So they could just be forgotten about. And then you could just reduce this fraction and you would get what we would call an end behavior model. Now, here's the thing. This trick can only be done with constant numbers. Cannot be done with variables. If there's other variables, then in order to get your end behavior model or end behavior asymptote, you will have to use polynomial long division, which we will do in chapter 2. So for now, we will only be disregarding constant values. That means numbers that don't have x's, okay? That allows us to look at graphs and equations and match them up without really knowing much about them. This first graph, or first function, excuse me. What do you notice about it? It's bottom heavy. Since this first one is bottom heavy, we automatically know that it has a horizontal asymptote, and specifically that horizontal asymptote is going to be the x-axis at y equals 0. So then you look at your 4 graphs, 1, 2, 3, 4, and you say which one of them is getting closer to the x-axis as x gets further away from 0. You guys can just say it. As you go to the far left and the far right, which graph gets closer and closer and closer to the x-axis? Double I, graph 2. This one is approaching this horizontal asymptote. And you actually already saw a graph like this a few days ago. Right there when we were talking about boundedness. Graph B, well, equation B. What should we be noticing? Equal degree. Yes, we have the same degree on the top and bottom. And since we have the same degree, we will be guaranteed to have a horizontal asymptote, and it's found by division. Leading coefficient over leading coefficient. So that is going to be y equals leading coefficient. 3 over 1, which is just 3, because there's a 1 right here. So you're looking at the 3 remaining graphs, and you tell me which one's approaching the line y equals 3 at the far left and far right. The first graph, he says, i.e., yeah, the first graph. It's approaching the line y equals 3 at the far left and far right. And we'll get closer and closer and closer to it. Conveniently, for my notes, the first 2 pictures and first 2 functions are taken care of, so I can scoot it up. Awesome. Now, both of these are top-heavy. That means neither one of them has a horizontal asymptote. So what we do in order to find our in-behavior model is we say, well, if x was large enough, if x was sufficiently large enough, then this equation is essentially equal to 3x to the third over x squared. We're forgetting about the plus 1 because it's going to mean very little when x is huge. And this reduces perfectly to 3x. That is a linear equation with a slope of 3. So we have graph 3 and we have graph 4. Which one of them appears to be approaching the straight line y equals 3x? Yeah, graph 3 does. And the further out we zoom, the more that line is going to look like y equals 3x. Which I know, obviously, that means that this one is part D, but I do want to show you the math that gets us there. Remember, when we're talking about in behavior, we're talking about extreme values of x. Extreme values of x discount constant numbers that do not have variables on them. This one would reduce to 3x squared. So x is 1, we'd be at 1 comma 3. So we'd be at negative 1 and 1 comma 3 like this. We're going to get this very steep looking parabolic asymptote like that. So this one was graph 3, and this one is graph 4. What do you guys got for me? Got any questions? Too easy? Or it just makes sense? You don't need a calculator. Yeah. And that's the thing. I know this is a really large section, section 1.2, but its whole purpose is for you to know basically what a graph looks like without ever touching a calculator. Everything we did, increasing, decreasing, concavity, and asymptotes, all of that tells you this is essentially what a graph looks like without me touching a graphing calculator. Yes, Diane?
So, vertical asymptotes, you go x equals?
Yes, and the reason why vertical asymptotes are x equals is because, let me find one that's already drawn up. Could have sworn I had some on here somewhere. Where'd that one go that I referenced a minute ago? Oh, there it is, right there. See these vertical lines? what axis do they run through? No, this one right here. Because the x-axis is the only axis they touch, it forces them to be x equals whatever the number was that they went through on the x-axis. Right. So the only reason why horizontal happens is because the graph is able to approach a number. But when they're top heavy, basically they can hear that while I'm explaining. The video's still running. Anyway, top heavy functions, remember I said if it was a race to infinity, the top would get there first, which means we can't actually approach a number. Well, the reason why they say y equals is because they are still functions. So the asymptote itself is a function. So its y values are determined by what x was plugged in. So when you say y equals a number, it's going to be horizontal because it can only touch the y-axis. But if you say y equals and it includes any x's, we're just going to have some kind of line or curve. Based on what the x is, we'll know what the y was for that quote-unquote asymptote. Cool? All right, good questions. Thank you, nerds. Oh, hold on. There it is.